Before I start with the topic of today's lecture, namely how to embed Marlowe in Haskell or JavaScript or other programming languages, I want to make an announcement. We want to set up a mock incubator for this course, for the participants of this course, where the idea is that we give you 3 example business cases that we hope or think might profit from applying Marlowe to them. And the idea is that you hook up with other participants in the course and then in groups pick one of those business cases. And in particular, there will be a sheet for you to sign up to this. Apart from this being a great exercise, we will also grade all your proposals. And in the last lecture, I explained the most important constructs of the Marlowe language and showed a couple of example contracts using those constructs. And we mostly worked in Blockly. I also showed you how to work directly in Marlowe. And in this lecture, I want to concentrate on the other 2 ways that the Marlowe Playground offers to develop Marlowe contracts, namely using JavaScript or using Haskell. And I will try to explain why one would like to do that and what the advantages are and what things you can do choosing one of those 2 options that you can't do in Marlowe directly or in Blockly. One of the great things about Marlowe is that you don't really need experience in programming in order to use it. It has been designed, for example, for people with a background or an interest in finance that want to write financial contracts for the blockchain. And it's perfectly fine for most contracts or for simpler contracts to just use Marlowe or Blockly directly. And we saw how to do that last time. But there are advantages using a more powerful programming language. So this lecture is mostly for those of you who do have some programming experience or are willing to learn a bit of programming. Now, most people probably have more experience with JavaScript, but nevertheless, in this lecture, I want to mostly concentrate on Haskell, but everything I do in Haskell in principle is also possible in JavaScript. It's just that I personally am much more experienced in Haskell and feel more comfortable in it, so it's easier for me to do the examples in Haskell, but everything that I show you in Haskell is also possible in JavaScript. And I, of course, also will show you a bit of JavaScript code. There's one distinct advantage of using Haskell when you do Marlowe, namely that Marlowe itself is written in Haskell. So the Marlowe language itself is a so-called DSL, a domain-specific language implemented in Haskell, which of course means that the integration of Haskell and Marlowe is particularly smooth. But nevertheless, doing it in JavaScript is also very doable and has some nice support. I also should mention that it's not limited to these 2 languages, to JavaScript and Haskell. In principle, all you need to do is generate some JSON object, some JSON data that represents the Marlowe contract. And you can use whatever programming language you like that is able to emit some JSON, which in principle is every programming language. So you could just as well use Python or C# or Java. JavaScript and Haskell happen to have special support in the playground, but in principle, there's nothing to stop you from using any other programming language of your choice. So if in the playground we click on Start in Haskell, then a very simple Haskell program opens. And this program just produces the contract close, so the simplest possible Marlowe contract. So there's some boilerplate here. What does this program do? Well, it's in a module called example. It imports the definition of the Marlowe language. And then it has a main program here. So this whole thing is actually an executable that you could run. And all that executable does is it prints some JSON to the console. And where does it get this JSON? Well, down here is the definition of a Marlowe contract called contract. In this case, it's just close. And then this print JSON function is used to take this Marlowe contract and print it in JSON format. And this is all this program does. And as I said, you could use any programming language to generate this JSON. Once you have the JSON, you can go ahead with the contract. And the Marlowe contract is just a value of type contract of this Haskell type. So one thing I can do is I can copy paste another Marlowe contract there. So let me just reformat this. So I just took a Marlowe contract and as is put it there. And we can compile. If all goes well, we won't get an error message. So it's green, that means there was no error. And then we can send it to the simulator. Here we get the Marlowe contract, the result of executing this Haskell program. So the Haskell program prints JSON to the screen that represents a Marlowe contract, and this Marlowe contract is then displayed here when I send it to the simulator, and I can simulate it. So in this case, this program is actually a possible solution to the homework I posted last week. So the idea was we have two participants, giver 1 and giver 2, that are both supposed to make a deposit. And the order in which those deposits are made is arbitrary. So either of the two can start, and then the other has to also make a deposit. And then once both have made a deposit, the money is paid to a third party, a receiver. So I can set the amount here. Let's say 100 ADA, 100 million Lovelace, start the simulation. And now there are two possible actions. Giver 1 can make a deposit or giver 2 can make a deposit. If, for example, giver 2 makes it, then giver 1 can also make it. And then payments are made to the receiver wallet. So by just taking this Marlowe and pasting it here, I now have it in this Haskell program. Of course, if this was all I ever did, just write a large Marlowe contract here directly in Haskell, then I wouldn't gain anything from using Haskell. So why would I want to do this? Well, the point is that this is just a value of the type contract, the Haskell type contract. And I can now use Haskell, arbitrary features of Haskell, to manipulate that value and to make it easier to write this value. Before we look into that, I just want to point out that here we also have this generated code tab. Right now there is nothing, so I need to compile again to get something there. And once it's compiled, here the generated code is shown. And in this case, it's exactly the same that I wrote here, because nothing happens. I just write directly value of type contract here, and all the program does is basically serialize it to JSON, print it to the screen, and then here in the generated code, we see exactly the same Marlowe program that we wrote down here. So this is obviously not very interesting. So what can we do to make it more interesting and to actually use the fact that now we are in Haskell? So one of the things that Marlowe doesn't offer is avoidance of code duplication. So there's nothing like a subcontract or subprogram or subroutine in Marlowe, where if several branches of your contract share code, you can only write it once and then use it several times. Whereas, of course, in normal programming languages like Haskell or JavaScript or others, this is an important feature. And if we look at the contract, the way it works is it has these two cases that giver 1 makes the first deposit. So this is this here until here, or that giver 2 makes the first deposit. And in both cases, once both deposits have been made, we make this payment where both giver 1 and giver 2 pay to the wallet of the receiver. So this block here, this pay block, for example, is exactly the same in both cases. So it doesn't matter whether giver 1 made the first deposit and then giver 2, or giver 2 made the first deposit and then giver 1. In both cases, afterwards, we do this payment. So this would be a typical situation where in normal programming, we would try to avoid this duplication of code and instead only write it once and then reference it at the two spots where we actually want to use that. So we can do the same here in Haskell. So in Haskell, the way you do a local definition, or one of the ways you do it, is with where. So we can say where and then give it a name. So we can, for example, say pay. call it pay. It's of type contract. And I just copy paste this part here that's duplicate. Just reformat it a bit. Actually, let me switch key bindings to Vim because I use Vim, so I'm more familiar with how to do that. Okay, so we have now pulled out this part that was duplicated, given it the name pay, and now instead of using it here, we can replace the two occurrences with the reference to pay. It still compiles. And if we look at the generated code, it should be exactly the same as before. So in particular, this pay here has been filled in again. So we haven't changed the actual Marlowe contract. We have just changed the way that we use Haskell to generate this contract by using this local definition here. Now we can look for other occurrences of code duplication. So for example, we have 4 deposits and they're all very similar. So the first 2 roles are always the same. Giver 1, giver 1. Here, giver 2, giver 2, giver 2, giver 2, giver 1, giver 1. So in each deposit, it always goes from one role to the role's internal account. And the amount and token are also always the same. So we have 2 cases, the one with giver 1 and the one with giver 2. So both occur twice. So here we can, let's call it deposit, and let's make it a function that takes a party. So this will be giver 1 or giver 2. And in this case, the type of this thing is not a contract. It's a so-called action. So the return type of this function will be an action. Let me call the party P. Paste this here. So we replace those 2 occurrences here of parties with our P. And incidentally, this is just ADA, and there's an abbreviation for ADA, so we can just use ADA. Actually, now it's no longer necessary to write it like this, so we can write it more compactly in one line. It's just the same. And now using this function, we can replace all our deposits. So this is just deposit giver 1, pay, and so on. And it still compiles, and it should still be the same code as before. We have giver 1, giver 2, giver 2, giver 1. So what else can we do? Well, if we check, there are now these 2 cases where giver 1 first deposits, then giver 2, and the pay happens if both deposit, or giver 2 starts, then giver 1, and the pay happens if both deposit. So these 2 cases are almost identical. The only difference is the order here between giver 1 and giver 2. So we can pull that out as well. Let's call it deposits. So it takes 2 parties. It results in a case. Let's call the parties P1 and P2. Okay. And now I can use that here. And it still should result in exactly the same code as before. So one last thing we might do, it won't shorten it this much, but we have these strings here that we repeat, giver 2, giver 1, deadline, deposit, and so on. So what I'll do is, at the moment, this is just a value of type contract. I just put these parameters, the role names, giver1, giver2, and receiver, as well as this time parameter and the deposit amount into parameters for the contract. So it takes three parties, which will be giver1, giver2, and receiver. It takes one value, which is this constant param deposit, and it takes one timeout, which is our time param deadline. So let's give those parameters names. Giver1, giver2, receiver. Let's call it amount and deadline. I can replace that everywhere here. I also can replace this by ADA. Now, of course, that won't compile because now contract suddenly takes these 5 parameters. So let's add them here. After we have looked at Haskell, let's now look at the same example in JavaScript, although I will spend less time going through it because it's virtually the same. So if we start with JavaScript, then first we get some imports from Marlowe.js, and we see all the constructs that we have spoken about are also available here in JavaScript. And the way this works is that we have this function without parameter of type contract that returns the contract. So this basically replaces the main function in the Haskell version. So where the main function of the Haskell version prints a contract to the console, here in JavaScript, the way JavaScript returns the contract is via such a function without arguments. So this simplest program, if we compile it, would unsurprisingly just generate the close contract. And actually writing contracts here in JavaScript is very similar to Haskell. So we could just start, for example, with when, and we also get very nice autocomplete. So we see when takes 3 parameters, an array of cases, a timeout, and then the continuation, so the contract that happens if the deadline is reached. So I could now start, for example, with an empty array, and now I see I need a timeout. So for example, I could use time parameter again, and again I get nice help telling me that now I need a string, so the name of the parameter. And finally, I need this continuation contract. So for example, I could use close. And now this would also be a valid contract. It generates this Marlowe. And of course, now I could continue implementing our contract by doing the 2 deposits here. I could start with case that takes 2 arguments, the action and the continuation. So let's start with deposit and so on. Now I don't want to enter the full long Marlowe contract here in JavaScript, but you get the idea. And actually the support with auto-completion is really very nice. It's actually nicer than in Haskell. So you always get help, context-sensitive help. So instead of repeating step by step what I did in Haskell, I'll just show you the result. And this is also saved on a public gist. So we will leave the link to that in Canvas. So this is virtually exactly the same simplifications and refactorings that I did in the Haskell version. So I have a parameterized function that produces a contract that I call double pay with the same parameters we had in Haskell. So the 3 parties, the amount and the deadline. Then I have helper functions here, pay and deposits. Then using these helper functions, it's easy to write the actual contract. It's just one when with 2 cases, deposits giver1, giver2, and deposits giver2, giver1, deadline and close. And then finally, by instantiating the parameters to the values we use. So role giver 1, giver 2, receiver, the deposit param and the time param, I get exactly the same contract that I had before. So I can compile, and this should be exactly the same Marlowe contract we have looked at before. And it seems to behave the same as it should. So it's really a matter of taste whether you prefer JavaScript or Haskell. I personally prefer Haskell, of course, but if you are more familiar with JavaScript, then it's perfectly okay to write your Marlowe contracts in JavaScript. As you can see, you can do basically the same simplifications that I showed you in Haskell, also in JavaScript, and end up with a version of the contracts that's just as short as the Haskell version was. So to summarize, we can write Marlowe in JavaScript and in Haskell, and the principle is the same. You write a Haskell or JavaScript program that produces a Marlowe contract. And you can use all the features of the host language, Haskell or JavaScript, in order to produce that contract. So in particular, you can make use of features like local definitions, helper functions, and so on to make that task easier and make it shorter. And of course, by preventing code duplication, you also prevent mistakes. I mean, it's a common mistake to want to write the same code, but then actually not ending up with the same code. So by refactoring that and pulling out the common parts, you avoid that common source of mistakes. And as I also mentioned, you are not restricted to JavaScript or Haskell. So in principle, you can use any language you like as long as you can produce some JSON. So if you produce JSON, that's serialization of valid Marlowe contract, then you're fine, and it doesn't matter what language you use to produce that JSON. In the example I showed you, we used Haskell or JavaScript to drastically reduce the amount of code we had to write by removing code duplication. But the end result, the resulting Marlowe contract that was produced by our Haskell, respectively JavaScript program, was exactly the same that we wrote before, for example, in Blockly or in Marlowe directly. So in that sense, we didn't gain anything. I still think, especially for more complex contracts, it's much easier to do it like this in Haskell, JavaScript, or another language. But nevertheless, the result we got was exactly the one we could have written in Marlowe directly. So now I want to talk about use cases where actually you need to do it like this in order to achieve your objective. And that is the case when the structure of your contract depends on the specific instantiation. So the contracts we wrote, especially this example contract, had two parameters, the deadline and the deposit. So in that sense, it was not just one contract, but a template for contracts. You can choose a specific deadline and a specific deposit amount, and then instantiate your specific version of the Marlowe contract, the instance of your Marlowe contract, to those values of the parameters. But what if the structure of the contract itself is supposed to be parameterizable? So in our example, we had these two givers that have to deposit the same amount of money into the contract. And then once they both do that, the money is sent to the receiver. So let's now assume that you want to generalize that. So you want to maybe have 3 givers or 5 givers. So the logic should still be the same. So given a fixed number of givers, which can be 2 or more, those givers have until the deadline to deposit a given amount into the contract in arbitrary order. And once all of them have done it, the receiver gets all the money. Now, of course, you could do that for any specific number. So we did it for 2 givers. Of course, you could do it principle for 3 givers or for 4 givers or for 5 givers. But of course, it would become more and more complicated. Now we needed two cases in our when statement, in our top level when statement. One for first the giver one deposits, then giver two, and another one for giver two, giver one. Now, if you have three givers, then there are already six possible orders. Like the previous examples, I could do this in the playground. And of course, the playground has a lot of advantages. For example, you don't need to install anything. You just open the playground in your browser and you can immediately start developing Marlowe contracts and then also immediately send them to the simulator and try them out. So that is really nice. However, I want to show you an alternative that I personally prefer, namely how to write Marlowe contracts locally. We have a GitHub repository accompanying the course. It's input output -HK Marlowe Pioneer program. We'll put the link in Canvas. And at the moment, there are just some code examples in there. So the ones I showed you at the beginning of this lecture from last week, but now in Haskell. And this double pay and double pay refactored is what we just looked at in Haskell, how to refactor this example contract and make it much shorter and nicer. And finally, there's this multi-pay that I now want to show you. So if you clone this repo and then change to the folder in your terminal, then you can cd into the code folder and do a cabal build to build all the example programs. In my case, I've already done that. If you do it the first time, it will take quite a while because there are a lot of dependencies. So the advantage of doing it like that is that you in particular now have all the normal Haskell tools available at your disposal. I mean, one thing you can do is you can actually run one of those programs. So for example, there is simple payment pay. That was the very first example we looked at, where just one party deposits money, which then gets paid to another party. And if we execute it, what I told you before, that all these Haskell programs do is they print the JSON version of the Marlowe contract to the screen. So you can see that here in action. So that's, of course, not very interesting. So why I particularly like developing locally is because now you have the REPL, the Haskell REPL available. So if I do a cabal REPL exe simple payment pay, I end up in a REPL and now I have the usual interactive tools available. So for example, I can ask for information for the type contract, the type of Marlowe contracts, and then I get all the constructors, close, pay, if, when, let, assert. So I want to show you how to implement this multi-pay contract where the number of givers is arbitrary in Haskell, doing it locally. But again, you could just as well do it in the playground. I just wanted to show you an alternative way of developing Marlowe programs in Haskell. Of course, it's also possible to run a local version of the playground, but I'm not going to show that in this lecture. I already wrote the code, so I don't want to spend too much time on that because this is, after all, a Marlowe lecture and not a Haskell lecture. And most of you are probably not familiar with Haskell anyway. So the main point I want to get across is that by using a programming language to emit Marlowe code instead of typing in the Marlowe code either directly or in Blockly, offers the advantage that by doing that, you can have something like templates that are much more flexible than what you can achieve in Marlowe by using parameters for values or times. It's already nice that we have these parameters, but if you want variability in the structure of the contract itself, then you need more powerful tools. And you can achieve that by using a program that generates your Marlowe contract for you. So that's the main point. And again, you don't need to use Haskell. You can use your favorite programming language. And if you're not a programmer, you can also, of course, always write Marlowe directly. So This is more for power users. So let's start a REPL for this example. So that's called multipay. And let's also look at the code. So this is the normal structure of a Marlowe program. Here's the main program, and this is the interesting function. So contract now, before we had three parties, giver one, giver two, and the receiver, and then the deposit value and the timeout, the deadline. So now I replace the two givers with a list of parties. So the idea is it can be arbitrarily many givers, and this should produce an appropriate Marlowe contract then for an arbitrary number. So I can demonstrate it if I call cabal run on multipay now. This will be a contract for three givers. If I change this here and in the main program remove giver 3 and run it again, we'll have to recompile, but that should be fast. And now this should be the original contract, the example we looked at in the previous section. They can also go crazy and add two more givers. The names, of course, are arbitrary. Don't have to call them giver 1, 2, 3, 4, 5. Now we see the contract is really, really long. So that's what I mean by structurally different. So by using this Haskell program that generates a Marlowe contract, we can, by simply changing some parameters, generate really different Marlowe contracts that are structurally different. So this one here for 5 is much longer, because for 5 deposits, you have 120 possibilities in which order they make their deposits. So let's look at the code. So the interesting function is this contract function. And what's the idea? So in principle, there are two parts. First, we have to wait for all the deposits. And once all the deposits have been made, each of the internal accounts that now contains an individual deposit has to send the money to the receiver. And for this first part, what we need at the top level is a when contract, and then we need cases for all possibilities. So for a list of givers, what are the possibilities? Well, each giver in the list could be the one that makes the first deposit. So what we need is, given a list of givers, we must somehow produce a list of possible first givers and the rest. And that's why I wrote a helper function here. So that's one of the nice things of using a programming language to generate your Marlowe code for you, that you, for example, can have these helper functions. We saw those before, like this deposit in the previous example. So this is the same actually, but it can also be like general purpose helper functions that are not local to the function you're writing, but you could even put that in the library. You could even imagine assembling a little library of useful utilities for generating Marlowe programs. So this picks function, just very briefly, giving a list, it produces a list of pairs of one element in the list and the other elements. So we can try that out in the REPL now. That's so nice about doing it locally. So I can just do picks and now give an arbitrary list. Let's say a list of integers. So let's say 1, 2, 3, 4. And just to make Haskell happy and unambiguous, let's say that it's of type int, doesn't matter. And that will give me this list of 4 elements. So given these 4 numbers, I could start with 1, and these are the rest, 2 through 4, or 2 could be the first, and then 1, 3, 4, others 3, 1 to 4, and 4, 1 to 3, and so on. And of course, I can have more elements, and then there are accordingly more possibilities. So that's this helper function I wrote here, and I'm using that now. So on the top level, I call this helper function go initially with all givers. And now there are two cases. First case is that the list is empty. So there is no giver left. So all of them have made their deposits, or there were no givers to begin with. So in that case, I go to the second part where the payments happen. But if there is at least one giver left, then, so this is Haskell list comprehension. So I loop over these picks. Picks prime is just where I call my helper function. So now I have these possibilities with which giver to start and all the remaining ones. And now I just construct a case where the action is that the one that starts deposits. This is our old deposit helper function. And then recursively, I continue with the rest. So for example, for 3 givers, this picks would be, we can try it out. A 3-element list, which tells me, okay, in the case of 3 givers, giver 1 could start and 2 and 3 are remaining. Giver 2 could start and 1 and 3 are remaining, or giver 3 could start and 1 and 2 are remaining. So in this outermost loop, I would construct a when with 3 cases. And the 3 cases are 1 makes a deposit, 2 makes a deposit, 3 makes a deposit. And then in that case, the continuation now recursively calls go with the remaining ones. So I have givers 2 and 3 left in this case. So now again, there are 2 possibilities that 2 makes the next deposit or 3 and so on. In the last case where 3 starts, the remaining ones are 2 and 3. And there are also 2 cases that the next deposit comes from 1 or from 2. Okay, and this will take care recursively of all the necessary deposits. And finally, we call this payments function, which again gets the full list of all givers. And this payments, again, a recursive function. This argument denotes the givers that haven't paid yet. So if that's the empty list, if everybody has paid, we are done and we close the contract. And if there is at least 1 giver left, we make a payment from this giver to the external wallet of the receiver about the amount in ADA, and then recursively do the payments for the remaining givers. For homework, I wrote a contract where the implementation at the moment is just close, and I would like you to implement that properly. So this is, I think, much easier than this multi-pay contract that we looked at. But nevertheless, for people without programming experience or much programming experience, it might be a bit hard. Of course, you don't have to do this in Haskell. You can also do it in JavaScript if you like. But what you can also do if you find this too difficult is go through the contracts from last lecture. These simple payments or choice if and so on, and try whether you can do something similar to what we did here with the double pay. So just try to simplify those programs. Of course, they were simple already, but maybe you find a way to write them in a nicer form in Haskell or in JavaScript. Okay, so the idea here is it takes a couple of parameters. So the rough idea is that you have a bank and a client, and the bank first makes a large deposit, and then the client makes a couple of small deposits. And if the client makes all his deposits, all the expected ones, then he will get all the money in the end. So the deposit of the bank and his own deposits back. If, however, at some point he stops making deposits, then the bank gets its own money back, but also all the deposits that the client has made up to that point. So the parameters are the first and the second are the party for the bank and the client. Then the number of rounds. So that's actually what makes it interesting. So the number of deposits that the client is supposed to make, because that means that the structure of the Marlowe contract will be different. So if you have a different number of deposits here of rounds, then the contract will also be different in its structure. So it's not just values like times or values that change, it's the contract itself that changes, because then more deposits by the client are expected. Then this is the amount that the client has to pay in with each deposit. And the rule is that the bank has to pay the total. So if it's 5 rounds and this here is 10 ADA, then the bank would have to pay 5 times 10 equals 50 ADA. The first timeout is the timeout until when the bank has to make his deposit, and the second timeout is the timeout until when the client has to make all his deposits. So I can demonstrate that for this special case here. So we have party bank is called bank, the party client is called client. There will be 5 payments expected by the client, each over 50 ADA, and the time parameters are just parameterized. So it's called bank deadline and deposits deadline. I have that here in the playground. So I have to specify these 2 deposits. Of course, realistically, they would be much farther apart than just 5 minutes. So let's try it. So the first action is the bank must deposit 250 ADA. So and if the bank does that, so now it's up to the client, and he can make deposits 5 times. 1, 2, 3, 4, 5. And if he has done all the 5 deposits, then the bank pays the original 250 to the client. If, however, the client stops, let's say after 3 deposits, the client stops and doesn't make a further deposit, then all the money that he already paid, in this case 150 ADA, go to the bank. Yes, and so the idea is to make that variable. So here it was 5 rounds, 5 deposits, but I can change that and generate a Marlowe contract for like 10 deposits or 3. So I hope you enjoy this exercise. I hope it's not too difficult. And as I said, if you want, you can try to look at our earlier contracts and do them in JavaScript or Haskell and try to simplify them somewhat.